Good day, sir. For this video, I will summarize what I've learned in ECE 3211L Control Engineering Laboratory. So overall, this subject taught me that control systems are about making a system behave the way that we want it to behave. So in simple terms, we have an input, a plant, a process, an output, and sometimes a feedback path. And the controller compares what we want with what we actually get, and then use the error to improve the response. So the first major lesson was how to represent systems in MATLAB. So in Lab 1, I learned that systems can be connected in either series, parallel, or feedback form. And so series means one system's output becomes the next system's input, and parallel means two systems receive the same input and their outputs are combined. Feedback is the most important because the output is returned to the input to correct errors, and this overall helped me understand that block diagrams are not just drawings. They can be converted into actual mathematical models using MATLAB commands such as TF, ZPK, series, parallel, and feedback. So, in Lab 2, I learned the purpose of Simulink and Simscape. Simulink is useful because it lets us build dynamic systems visually using blocks. Simscape goes further because it lets us model the physical systems using actual physical connections. This made control systems feel more practical because instead of only writing equations, we can also simulate systems in the way that resembles real engineering setups. So, the next important topic is Lab 3 was transfer functions and time response. So, I've learned that a transfer function is the ratio between the Laplace transform of the output and input. So assuming zero initial conditions, in the lab we manually derived a transfer function from a differential equation and verified it using MATLAB. So this showed me that the equation, the transfer function, and the simulation should all describe the same system, and I've also learned how to analyze the step response using the settling time, rise time, peak time, and percent overshoot. So these are important because they describe how fast and how stable the system response is. So after that, I've learned about poles and zeros. Zeros come from the numerator of the transfer function, while poles come from the denominator. So the poles are especially important because they determine the stability and shape of the response. And in Lab 4, the main lesson was that if all poles are in the left half plane, the system is stable. If a pole is in the right half plane, the system is unstable. If poles are on the imaginary axis, the system becomes marginally stable and oscillatory. So the pole location tells us basically whether the response will decay, grow, or continue oscillating. So, in Lab 5, I've learned about the performance specification. So, a second-order system can be described using natural frequency, damped frequency, and damping ratio. The damping ratio is very important because it affects oscillations and overshoots. A small damping ratio creates more oscillations and higher overshoot, which means a larger damping ratio reduces oscillation, but the response can become slower. So, this taught me that control design is always a trade-off between speed, stability, and accuracy. So, moving on to Lab 6, we studied root locus. Root locus is basically how the closed loop poles move when the gain k changes. I learned that the location of the closed loop poles determine the system's behavior. So in Lab 6, one example showed that with one gain value, the pole could still be on the right half plane, making the system unstable. But with another gain value, the pole moves to the left half plane, making the system stable, and this made root locus useful because it helps us choose a controller gain based on the desired response. So in Lab 7, I've learned that sometimes changing gain alone is not enough. If the desired closed loop pole does not lie on the root locus, then no gain k can place the pole exactly there. That is why compensator is added. The compensator reshapes the root locus by adding poles or zeros. So in our activity, a single zero was not enough to satisfy the specifications, but adding two zeros improved the response. And the key idea is that compensators help the system meet design requirements such as settling time and overshoot. So finally, Lab 8 focused on PID controllers, and I've learned that the PI controller uses proportional and integral action. So a proportional part basically reacts to the present error, while the integral part helps remove the steady state error. So a PID control adds derivative action, which predicts the trend of the error and can improve transient response. However, I also learned that PID is not magic. A PID controller cannot always meet all design specifications because real systems have limitations such as saturation, delays, noise, and unstable dynamics. So, to summarize, this subject taught me how to move from theory to simulation and design, and I learned how to model systems, analyze their time response, check stability using poles, design using root locus, and improve performance using compensators and PID controllers. And the biggest lesson for me is that control engineering is not only just about making a system work, it's also about making the system respond correctly and predictably. And as a future engineer, I realized that control systems are not just equations or simulations. They are about designing systems that are safe, stable, and reliable in real life. This subject taught me to think carefully about how a system responds, how errors can be connected, and how performance can be improved. And moving forward, I will apply these lessons in designing smarter and more dependable engineering solutions.